From orbit, the planet looks composed and ancient, a blue sphere veined by clouds, rimmed by a faint electric edge where daylight meets night. City lights beat along coasts, then vanish as the Earth rolls. We admire it for its permanence. We teach its mountains and oceans as if they were chapters in a book that never changes. Yet the first lesson of the crust is not comfort. Earth forgets. It builds and destroys its own pages, then writes new ones on the same paper. There is a device that tried to argue with that forgetting. Engineers in the north lowered a steel string into a borehole more than 10 kilometers deep. Instruments chattered. Cables sang. Rock groaned like a living thing. The numbers returned heat that rose faster than expected. Pockets of fluids where none should be. Microfossils where life seemed impossible. We dug toward memory and found a different kind of silence. The silence was not empty. It was thick with processes that do not care about us. Now lift your eyes from the drill to a map that shows the ocean floor as bands of color. Long seams run like scars across a single global wound. Along those seams, the planet prints new crust. It prints in dark basalt, striped by magnetic ink that flips whenever the planetary field wanders. The record looks perfect at first glance. Then the conveyor starts. Fresh rock slides away from the seam, cools, is buried, and after a short life, it is dragged back inside. The ocean pages are always young. The archive resets itself each time a new page is bound. Here is the paradox. Civilizations carve monuments, leave cities, dump metals, and change the chemistry of air and water, but the surfaces that hold those signatures are temporary in the oceans and battered on land. Rivers shave continents. Glaciers mill valleys. Volcanoes bury landscapes. Subduction eats the seabed. If a city rises on the shore and falls to the tide, the mantle may digest it without a trace. Earth is a historian who burns its own library to keep warm. We still read. We read with light, with sound, with chemistry. Satellites scan the sea surface for warm tongues of water that should not be there. Seismometers listen for the elastic snap that maps the underground in echoes. Ocean buoys feel the slow swell of heat and the slosh of currents. A hand-sized compass trembles when the invisible shield above us stutters. We piece together a biography from scraps. A crater rim here, a core of mud there, a thin layer that smells faintly of fire where no local fire should have reached, a diamond that rose carrying a tiny breath from a deep place. At the edge of a research ship, a technician pays out a cable and watches the seafloor pass beneath as stripes of polarity, black then white. Time marching left, time marching right. On the deck, someone asks a question. If our kind ever disappeared, how long would these stripes remember us? Is there a combinational marker that could outlive the reset? We look beyond geology for the answer and find a hint in the ocean itself. The Pacific sometimes breathes wrong. Currents that normally carry heat one-way stall, then reverse. Storm tracks shift. Droughts appear where rains were faithful, and floods where the ground once cracked. The breathing has a rhythm that is not a metronome. It is a stutter. When it stutters, the global climate wobbles. Fishers feel it first. Farmers count the lost days. Engineers adjust grid loads when rivers fall. We learn that small shifts in a vast system make large consequences, and that signals propagate into places that never expected them. In everyday language, a planet this active loses clues fast. A thing must be stubborn to survive here. A clay shard in a cave may last thousands of years. A mountain chain lasts tens of millions. But it changes shape every day. An ocean floor lasts less than 250 million years before the mantle asks for it back. So the search for deep-time evidence becomes a hunt for stubborn things, for isotopes that do not forget, for magnetized minerals that keep their first orientation, for molecules that should not be in nature at all. The deeper we look, the more patient the markers become. A volcanic ash layer baked hard carries a brief news flash from an eruption that darkened old skies. A stalagmite captures the pulse of ancient rains in rings as thin as breath. A core of Antarctic ice holds air that humans never tasted. old sunlight trapped in bubbles. We are collectors of difficult memories. We carry them into labs and let machines translate their grammar. But notice the rule the rocks keep repeating. The cleaner the slate, the faster it is reused. The mid-ocean ridges are young and efficient. The trenches are hungry. The continents are older, but restless, cracked by faults that let rivers and roots and heat alter the script. Now look again from orbit. Imagine every blue stretch of seafloor scheduled for recycling, every brown ribbon of mountain crumbling grain by grain into a delta, every delta sinking into a basin that will be overrun by a rising sea. What kind of message threads that moving maze and remains legible for a far future reader? We have one more clue, and it lies in places where forgetting slows. The moon is airless. Its dust is a quiet archive. Mars kept ancient surfaces. These are shelves that Earth does not have. We glance outward, not because we prefer other worlds, but because they may hold the mirror we need. If we changed our planet in ways large enough to echo through rock and ice, nearby worlds could keep a cleaner copy of the echo. The idea is not fantasy. It is a testable plan that respects what the interior of our own world insists on doing. There is a philosophical weight to this. A species that lasts long enough to understand how archives die must choose between two impulses. One impulse is to write louder in the hope of being heard. The other is to write gently in the hope of doing less harm. We live between those choices. Every brick and battery, every pipeline and data center, every farm and forest edge, every vessel and runway, all speak a language that geologists will translate long after the speakers are gone. The question is whether the translation will read like a warning or a boast. Picture a classroom with a flat stone on a table. A teacher places a magnet near it. The stone twists a needle. The children laugh because a simple rock suddenly becomes an instrument. Then the teacher turns the magnet, and the needle follows. The lesson is plain. The world remembers direction. It remembers in iron, and in ash, and in shells. But it remembers in its own idiom. If you want to leave a message that lasts, you must first learn the grammar of this place. Consider the instruments that decode that grammar. Gravimeters weigh empty space and find density. Magnetometers taste the iron memory of old flows. Mass spectrometers count isotopes like a banker counts coins, and a single odd ratio can betray an event that no witness survives. Core drills bite cylinders out of mud and rock. Time stacked on time, and every centimeter lowers you through seasons, through centuries, through extinctions. The tools are humble, but the ambition is not. Their readings become a language in which the planet speaks. Now follow that language into the deep crust where pressure seals secrets. Fluids migrate along fractures and record who passed by. Hydrocarbons crack and recombine. Sulfides precipitate around vents where hot water meets cold seawater at the ridges. Microbes dine in the dark on chemistry that sunlight never touched. A drilling crew loses a bit and pulls up a thread of clay that should not be there. A lab finds organic molecules in a place said to be sterile. The message forms in pieces. Persistent chemistry where change tries to rule. Turn to the shield that wraps this moving archive. The magnetic field rises from flow in the outer core. It is our weather against the sun. It also writes its own history into cooling stone. When the field falters or flips, lava that hardens that year keeps the new direction, and the seafloor becomes a barcode. We were not here for most of those reversals. The field logged them without an audience. If we hope to be legible, we must learn how that logging works. A second visual anchor can hold this thought. Stand at the foot of a fault scarp that cuts a desert plain. The face is clean, like a torn page. You can touch beds that were once flat and now end in air. A small finger of dark glass peeks from the wall, cooled from a friction flash during the last quake. Put a hand on the glass. It is not warm now, but it speaks clearly. This is how energy writes. Fast, local, undeniable. The same clarity is what we want from the signatures of civilization, but we must accept that our writing is slower, wider, and easier to blur. Ask what survives 100 million years that is not stone, not paper, not steel, not paint. The list is short. Ratios of stable isotopes, distributions of certain metals in sediments beyond what volcanoes can explain, the odd shapes of synthetic molecules that biology rarely builds, patterns in magnetism that do not match paleogeography, and off-world, a dust grain fused to glass by a transient rain of small debris made by machines. None of these prove industry by themselves. Together, they can whisper a pattern that is hard to fake. The big question waits here. How would you recognize an industrial civilization in the rock record without fooling yourself? The answer is not a single artifact. It is a suite. It is a test that refuses drama and accepts statistics. It looks for weak signs that align across domains: chemistry, magnetism, sediment texture, climate rhythm. If that suite lights up in the same interval on Earth and on a nearby airless shelf, the confidence grows. If it lights up in only one archive, the confidence falls. The humility is the point. A planet that forgets requires a method that refuses to rush. Hold one last early image. Night passes beneath a satellite. The continents glitter in lines and knots. The lights speak of fuel, of grids, of cities. Then the satellite changes cameras and stares at the invisible. The lights vanish. In their place bloom faint patterns in the sea, in the air, in the tiny movements of the field. These patterns are not ours alone. They are the breath and pulse of a world that was busy long before we arrived. Our work is to separate our handwriting from the background hum. Then ask what the separation means. You are invited to think like an archivist of moving ground. Ask the hard questions. How robust is a marker? How likely is a false positive? How do multiple weak hints become one strong voice? How do we keep track of uncertainty without losing courage? We will mark every speculation with care. We will prefer tests over tales. We will accept that some answers will be uncomfortable. If the past never held a city, the method is still worth building. If the past did, the method is the only honest way to notice. The stakes do not live in curiosity alone. The same techniques that could diagnose a dead industry can measure a living one. The same models that look for an ancient warming spike help us map and moderate the one we are driving now. The same habit of patient inference guards us from flattering myths about ourselves. The search for an old neighbor under our feet is also a search for a wiser self on the surface. There is an open loop to keep us honest. If we think we see a pattern, we will check it in 3 places: in the chemistry of sediments that should be bland, in the magnetic whispers of rocks that cooled in silence, and off-world, where dust keeps time better than our seas. Only when the same shape appears in all 3 will we even whisper the word civilization. That caution is the price of working on a planet that forgets. We will follow the seams that print new crust. We will watch the ocean breathe and misstep. We will go down the borehole and talk to the pressure and the dark. We will stand by the planetary dynamo that hums under our feet and ask what it protects and what it exposes. We will design a test that a future geologist could run on our layer without knowing us at all. A test that cares nothing for statues or myths, only for chemistry, magnetism, texture, and the rhythm of change. That test will send us outward as well, to dust that never rains and rocks that never subduct. If this frame sharpened your view, like and subscribe to the Quiet Universe channel. At first glance, the planet looks like a monument to endurance. Continents drift slowly, glaciers come and go, and mountains take lifetimes to erode. Yet beneath that apparent calm lies a mechanism that rewrites its own memory. The crust moves, melts, reforms, and moves again. What seems eternal to the human eye is temporary in geologic time. Every record the planet keeps, it later erases. A ridge in the ocean marks where 2 plates move apart. Lava rises, freezes, and spreads outward. Each layer captures a trace of the magnetic field at the moment it cools, like ink drying on a new page. Over millions of years, the crust travels away from the ridge until it dives into a trench and melts. The planet prints, reads, and then burns its own book. The process is slow, but relentless, and in its rhythm we begin to see a pattern. The Earth forgets not by neglect, but by design. Stand on a cliff where the sea has bitten the land into steps. The layers are thin, alternating colors of compressed mud and shell. A finger dragged across one edge touches shells that once floated in sunlight and mud that once rained down in darkness. The line between them is a heartbeat of time. Yet storms, earthquakes, and the slow lift of the continent threaten to mix those layers until nothing of their story remains. You can hold a fragment and still sense that the rest is lost forever. The mystery deepens when we look at the continents. While ocean crust is young, the cores of continents are ancient, sometimes more than 3 billion years old. But these oldest stones are no simple archives. They have been baked, folded, and scarred by countless cycles of heat and pressure. Minerals dissolve and recrystallize, creating new textures that overwrite the originals. The message is faint, but not gone, as if the planet itself were whispering through a wall of static. At its core, this is a cycle of forgetting and rediscovery. To put it another way, the planet's memory works like a palimpsest, a manuscript that is written, scraped clean, and written again. Geologists decipher it by reading what remains between the lines. A grain of zircon the width of a hair may outlast whole mountains, carrying within it the isotopic code of early oceans. It becomes a survivor of fire, a clue hidden in ash. Every fragment that resists melting is a letter in the language of deep time. Why does this matter? Because memory defines possibility. If Earth deletes its past too quickly, patterns vanish before they can be understood. Climate rhythms that could warn us of the future disappear. Biological experiments that failed or succeeded leave no trace. Each erasure shortens the archive that science depends on. We rebuild what we can from shadows. But there is always uncertainty at the edges. Imagine an old film reel playing backward. Scenes dissolve into white noise, the picture curling at the edges from heat. This is what happens to the planet's surface across millions of years. Volcanoes rewrite the scene. Glaciers scratch new tracks. Continents collide and edit their outlines. Somewhere in that flicker is the record of our own arrival. But how far back does the film reach before the frames are too damaged to recognize? To answer, scientists use time itself as a probe. Radiometric clocks in minerals measure decay rates of uranium, thorium, and potassium. The numbers reveal the age of events but also expose gaps. Some strata are simply missing, eroded before the next layer settled. Others are preserved only as isolated pockets under volcanic caps or inside fault-bound basins. Every missing chapter forces us to guess at what filled the silence. A field team in Namibia once mapped an area where the crust had been turned inside out. Rocks that should have been deep below the surface now stood above the desert like frozen waves. They were laced with veins of quartz that glittered in sunlight. Within those veins, tiny fluid bubbles held chemical signatures of ancient seas. The ocean that made them was long gone, but its fingerprints persisted inside crystals smaller than sand. The team called it a miracle of stubbornness, evidence that the planet sometimes forgets less than we fear. Yet the eraser is never still. Subduction zones along the Pacific Rim consume square kilometers of crust every year. Mantle plumes punch through Africa and the Pacific, creating new volcanic provinces that bury older terrains. Over hundreds of millions of years, the continents merge into supercontinents, break apart, drift, and meet again. Each assembly deletes coastlines, reefs, and rivers, reshuffling the archive like a librarian who never stops reorganizing the shelves. When we study those cycles, we begin to understand the planet's deep metabolism. Forgetting is not an accident, it is how the system stays alive. Without subduction, there would be no recycling of carbon or nutrients. without melting. The crust would become brittle and static, and life itself might fade. The same process that destroys evidence also sustains the conditions that make evidence possible. Forgetting is a form of renewal. Consider the scars left behind. Mountain belts crumble into basins, leaving a smear of minerals that hints at their former glory. Magnetic signatures in seafloor rocks show reversals of polarity, a kind of Morse code from the planet's magnetic heart. Impact craters, though battered, survive as ghosts in topography. Each is a frame in the reel, half erased but still readable with the right light. We learn to see absence as part of the pattern. At its most human scale, this story becomes personal. Cities are built on floodplains that move, on coasts that drown or rise. The walls we construct to outlast us may not last 1,000 years. Our species measures time by generations, but geology measures it by isotopes and mineral transformations. A carved stone in a desert may hold a name for a few millennia, but even the hardest granite yields to heat and stress. The monuments of our ambition are temporary punctuation marks in a sentence still being written. So the question grows sharper. What kind of trace could endure when even mountains vanish? Could we design a signal that the planet cannot easily recycle? Scientists and philosophers propose isotopic fingerprints, artificial minerals, or orbital debris as messages that might persist. But before we send any message, we must learn to read the planet's current language. If we cannot hear what Earth remembers now, we will not know what it will keep or discard later. A paleogeologist once described the planet as a vast film scanner that keeps rescanning a damaged reel, each pass erasing and redrawing parts of the story. The metaphor fits too well. Each tectonic shift is a jump cut, each eruption a flash frame, each glacial advance a new exposure. What we see on the screen is only the most recent edit. Beneath it, faint ghosts of older frames wait to be reconstructed. The chase for those ghosts is not purely scientific. It is also emotional. To trace the planet's forgotten past is to face our own fragility. We are temporary creatures standing on temporary ground, yet we hunger for continuity. The rocks show us that continuity exists, just not in the way we expect. It lives in process rather than permanence, in the repetition of creation and erasure. What seems like loss is the way the world breathes. We end this first investigation with a paradox. The Earth forgets almost everything, yet within that forgetting lies a form of memory deeper than any archive. It remembers through transformation, through the balance of destruction and renewal. To study that balance is to look at the machinery of time itself, a machinery that has been running since the planet cooled. The next step is to follow where that machinery is most visible, along the moving seams of the oceans where new crust is born and old crust dies. If the first truth of our world is that it forgets, the second is that it forgets methodically. The machinery of that forgetting lies beneath the oceans, stretching for tens of thousands of kilometers, unseen and continuous. There, at the mid-ocean ridges, the planet manufactures new crust. It does so not with explosions or drama, but with a patient outpouring of molten rock that cools, splits, and slides away. These ridges form the seams of the planet, the slow arteries of its memory. Picture a long cut in the ocean floor, a dark valley glowing faintly with rising heat. Along its spine, molten material wells up from the mantle. The liquid rock cools as it meets the freezing water above, solidifying into pillow-shaped basalt. As it freezes, tiny crystals align with the direction of the planet's magnetic field, recording its polarity like needles in a compass frozen in time. Then the crust begins to drift outward on both sides. A factory has begun its shift, printing new pages while the old ones are fed back into the machine. This motion defines the great conveyor of time. It is not mechanical, but it behaves like a belt, carrying material from the ridges outward toward trenches where it will one day be consumed. At any moment, half the seafloor is moving in opposite directions. The speed is slow, roughly the rate at which fingernails grow, but over millions of years that motion reshapes entire continents. The conveyor carries more than rock. It moves heat, chemicals, and even life. It sets the tempo of volcanoes and the architecture of climates. To understand it is to watch the planet breathing. Geologists map this process with magnetometers towed behind ships. As the instruments pass over the sea floor, they record alternating bands of normal and reversed magnetic orientation. These bands are symmetrical on either side of the ridge, like mirrored stripes on a barcode. Each pair marks a flip in the magnetic field. When those flips are dated with radiometric clocks, the pattern becomes a timeline. The discovery of that symmetry was the moment Earth science turned from speculation to certainty about plate motion. The seafloor itself carried the proof. In everyday language, the planet is recycling its skin. New crust is created in the middle of oceans and destroyed at their edges. That motion drags continents with it, because continents float on the same moving mantle. A single cycle from creation to subduction can take hundreds of millions of years. If we could speed up the film, the continents would seem to drift like rafts on a slow tide, colliding, merging, breaking, and drifting again. The world we know today is only one frame in that endless film. This movement does more than rearrange geography. It also governs how carbon and heat flow between the interior and the surface. Where plates diverge, carbon dioxide escapes from magma and enters the atmosphere. Where they converge, sediments rich in carbon are dragged downward and stored in the mantle. The balance between these two fluxes helps regulate climate over deep time. When spreading rates accelerate, volcanic outgassing increases, warming the planet. When subduction dominates, more carbon is buried, cooling it. The conveyor of time is also the thermostat of the biosphere. A ship's crew in the Pacific once followed the ridge crest for weeks, dropping sensors to measure temperature and chemistry in the deep water. They found hydrothermal vents, black smokers that belched superheated plumes laced with metals. Around them thrived ecosystems with no sunlight, powered instead by chemical reactions between seawater and rock. These vent fields reminded researchers that even in the planet's most mechanical processes, life finds a niche. The conveyor is not only a destroyer, it is a cradle. Why does this matter? Because the same motion that builds and buries land also writes and erases history. When two continents collide, the ocean between them vanishes. The sediment that once lay on its floor is crushed and transformed into metamorphic rock. Fossils are smeared, folded, and heated until they lose their shape. Yet the chemistry remains. Isotopes of strontium, neodymium, and oxygen preserve traces of the waters they once touched. From those ratios, we can rebuild the vanished ocean, a ghost restored by numbers. Simply put, the ridges and rifts are the planet's handwriting in motion. Each segment of ridge records a chapter of heat flow, magnetic behavior, and chemical exchange. The rifts mark where the next chapter will begin. The trenches are the closing punctuation marks, where sentences sink back into silence. In this moving grammar, every letter counts. The challenge for science is to read without stopping the motion. The contradictions within this system are striking. The same convection that keeps the surface dynamic also ensures that almost nothing survives unchanged. Yet some features resist even this cycle. Cratons, the ancient cores of continents, drift intact for billions of years, shielded by thick keels of cold lithosphere. These blocks are like stones carried on a flowing river. Stable but slowly tumbling, they remind us that while the conveyor moves everything, it does not erase all equally. A question arises. If the conveyor can transport continents across the planet, can it also influence life? The answer seems to be yes. The assembly and breakup of supercontinents correlate with major evolutionary events. When land masses merge, climates stabilize, sea levels fall, and species spread across broad ranges. When they split, isolation breeds new forms. Extinction and innovation move with the plates. The geology of rifts and ridges becomes the scaffolding of biology. In the present day, this system still breathes. Satellite measurements detect how the plates creep by centimeters each year. GPS stations along the boundaries shift their coordinates imperceptibly but steadily. Earthquakes mark the slip of locked zones finally releasing tension. Volcanic arcs trace the descent of crust back into the mantle. The conveyor of time has no off switch. It only changes speed. Think of the Icelandic landscape, where the mid-Atlantic ridge rises above sea level. There, you can walk from the North American plate to the Eurasian plate in minutes. Steam drifts from fissures, and the ground trembles underfoot. To stand there is to feel the seam of the planet tugging apart. Tourists pose for photos between continents, unaware that they are witnessing a factory floor. The lava they tread on today will one day sink into the deep Pacific Trench and vanish. Why it matters extends beyond curiosity. By decoding the motion of the plates, we understand how earthquakes cluster, how volcanoes feed on subducted material, and how continents may look millions of years from now. We also learn humility. Our settlements, economies, and histories unfold on terrain that moves beneath us. The stability we trust is a convenient illusion. The paradox returns. The conveyor keeps the planet alive, yet hides its past. It cycles material that could preserve our own story, grinding it to magma before it can fossilize. The record we seek lies in fragments caught between birth and destruction, in the ridges that have not yet cooled enough to sink and in the sediments not yet dragged below. The clock is always ticking, and the archive is always burning. To put it another way, the ridges are the gears of a clock whose hands we can never stop. Every revolution renews the crust, resets the record, and redistributes the elements that sustain life. The machinery is beautiful, and terrible, and indifferent. Its rhythm has been steady for 4 billion years, with only minor interruptions from impacts or mantle plumes. We live within that rhythm, brief notes on a score that began long before us. So the search for ancient evidence must follow the belt itself. If we can trace how heat, rock, and time move along the ridges, we may predict where traces of older worlds are most likely to hide, perhaps in isolated microplates trapped between larger ones, or in fragments of crust that escaped subduction. These are the planet's forgotten corners, the pauses between movements in the endless symphony of creation and destruction. The conveyor does not just move horizontally, it also breathes vertically. As ridges rise and cool, they draw water and carbon into the crust, storing it temporarily before releasing it back to the surface through volcanoes. Each breath takes millions of years. The modern atmosphere owes much of its composition to this slow exchange. Even the oxygen we breathe is balanced by the pace of tectonic recycling. Without it, the air would drift towards stasis and the oceans would grow poisonous. At the edges of continents, another story unfolds. Rifts tear at the crust, creating basins that fill with sediments and lakes, precursors to new oceans. The East African Rift is one such nursery, splitting slowly under a mantle plume. Within a few tens of millions of years, it may open into a new sea. The landscape is dotted with volcanic cones and salt lakes that shift color with mineral content. There, you can see the first breaths of an ocean forming, a preview of what our planet has done countless times. The Earth does not plan these transformations. They are the outcome of convection, density, and gravity. But in their persistence, they shape the trajectory of climate and life. When continents drift toward the poles, ice ages multiply. When they cluster near the equator, warmth dominates. Over deep time, the planet's surface acts like a kaleidoscope, rearranging its pieces into new mosaics of ocean and land. Each configuration alters the pathways of wind and water, the distribution of sunlight, and the opportunities for life to adapt or perish. All this motion adds up to a quiet truth. The world's stability is built on movement. The crust must flow, or the system collapses. Forgetting is built into the structure of the planet because the alternative is stagnation. The ridges and rifts do not simply erase, they renew. They provide the framework that allows a dynamic equilibrium to persist through eons. We close this chapter at the edge of a ridge valley, peering into the black water where molten rock rises to write another line of the planet's story. Around us, the seafloor glows with faint life and shimmering heat. Above, the surface waves hide all trace of the creation below. The next step is to follow how this conveyor of time connects with the atmosphere and the climate it drives, to see how the breathing of the oceans becomes the breathing of the world itself. The ocean is not silent. It inhales and exhales, though its breath is slow and measured in centuries. Warm layers rise and fall. Cold currents slip beneath. Gases dissolve. And the balance of life shifts with every change of temperature and motion. When we speak of climate, we are speaking mostly of how the sea remembers and releases heat. The ocean is the planet's lung, its rhythm a whisper that spans generations. Picture a cross-section of the Pacific. Along the surface, sunlight warms a thin layer of blue water. Beneath that layer lies the thermocline, a boundary where temperature drops sharply, separating the warm, light upper ocean from the cold. Dense depths, winds push the surface waters westward until they pile up along Asia, while along the coast of South America, colder water wells upward from the deep. This flow carries nutrients and carbon, creating a conveyor that feeds entire ecosystems. The system is balanced, but fragile. A small change in wind or pressure can flip it like a coin. Every few years, the rhythm falters. The trade winds weaken. The warm water that had gathered in the west sloshes back east, and the upwelling of cold water slows. Sea surface temperatures rise across the equatorial Pacific. Rain patterns shift across continents. This is El Niño. The ocean's hitch in breathing. To the meteorologist, it is a redistribution of heat. To the farmer, it is the difference between a harvest and a drought. The phenomenon connects distant lands through invisible threads of air and water. A storm in one ocean can echo as famine on another shore. Sensors across the Pacific now track this breath in real time. The Teo buoy array floats in long lines anchored to the seabed, measuring temperature, current, and wind. Satellites above detect small changes in sea height, translating them into maps of warm and cool anomalies. The result is a living image of the ocean's pulse. When the colors on the map shift from blue to red, we know the planet is taking a deeper, slower breath. When they fade back, we exhale with it. To put it another way, the ocean acts as the planet's memory of heat. About 90% of the excess warmth trapped by greenhouse gases ends up in its waters. That heat moves like a hidden current, sometimes locked below for decades, sometimes rising to the surface to shape weather across the globe. The oceans are both the buffer and the amplifier of climate change. Their breath can calm or intensify storms, nourish or starve fisheries, and stabilize or disrupt human life. In the Indian Ocean, a different rhythm plays, a seesaw of heat known as the dipole. One side warms while the other cools. Then they switch, off East Africa. This cycle can bring floods that rearrange river deltas. In the Atlantic, slower oscillations drive patterns of hurricane formation and drought. Every basin has its own tempo, yet they are all linked through the slow circulation known as the global overturning current, the deep breath that takes 1,000 years to complete. Warm water sinks near Greenland, flows through the abyss, and resurfaces in the Pacific. The planet breathes not just seasonally, but across millennia. Why does this matter? Because the breath of oceans governs the balance of carbon and the rhythm of life. When surface waters cool, they absorb more carbon dioxide, lowering the concentration in the air. When they warm, they release it. Tiny plankton, invisible to the naked eye, build shells from dissolved minerals and sink when they die, carrying carbon to the depths. This biological pump is part of the planetary lung, an invisible rain of particles that keeps the atmosphere stable. If that process falters, the breath changes character, and the planet warms faster. A clear example lies in the Paleocene-Eocene thermal maximum, a brief and violent episode 56 million years ago when temperatures spiked by up to 8 degrees Celsius. Sediments from that time show a sharp drop in the ratio of carbon isotopes, evidence that massive amounts of carbon were suddenly released. The ocean's breath quickened beyond control. Coral reefs died. Deep sea creatures vanished. And new species adapted to survive in hotter waters. The record of that event, preserved in layered mud and fossil shells, is a warning written in chemistry. Simply put, the ocean's breathing is not just a metaphor. It is a measurable cycle of gas, heat, and life that we can trace in numbers. Instruments aboard research vessels sample water columns for temperature and oxygen content. Satellites use microwaves to estimate salinity and wind speed. The data feed into models that predict future rhythms. Those models show that the breath is changing. The exhale is stronger. The inhale weaker. More heat remains at the surface, and the patterns of wind that guide the currents are drifting northward. At the scale of a human lifetime, these shifts feel subtle. A few tenths of a degree in ocean temperature, a few centimeters of sea level rise. Yet small changes in the breath of the ocean translate into enormous changes in the stability of weather. A warmer sea surface fuels more intense cyclones. A weakened upwelling reduces fish stocks that feed billions. The lung of the planet does not speak loudly, but when it changes rhythm, everything listening must adjust. On the deck of a ship in the equatorial Pacific, a scientist lowers a CTD rosette into the water. The circular frame bristles with sensors and sampling bottles. As it descends, the instruments trace a profile of the sea's interior: temperature, salinity, oxygen, fluorescence, all recorded in smooth digital lines. At 600 meters, a sudden spike in nutrients appears, a signature of water rising from the deep. The data confirms what the satellites suggested: the ocean is breathing in again after years of exhalation. The scientist smiles, not from relief, but from awe. Even in a warming world, the old rhythm persists, reminding us that the system is complex enough to defy prediction. The question arises, how far does this breath reach into the planet's interior? At the seafloor, hydrothermal vents release gases and minerals that react with the crust, altering its chemistry. Some of these reactions lock carbon in solid form for millions of years, storing part of the atmosphere underground. Others release methane and hydrogen that feed microbial colonies in darkness. The cycle between water, rock, and gas connects the biosphere to the mantle. The planet's lung extends far deeper than any wave. To a geophysicist, the link between ocean circulation and tectonic movement is more than poetic. The distribution of heat in the ocean affects how the crust flexes and where volcanoes rise. The melting of ice caps changes the weight on continental shelves, altering the stress along faults. The breath of the sea can trigger tremors and reshape coastlines. The feedback between water and stone is slow but certain, a dialogue older than any civilization. In everyday language, the ocean's breath is the story of energy exchange. The sun drives evaporation and wind. Wind drives currents. Currents carry heat, and heat shapes clouds that feed the rain returning to the sea. The loop closes, and the breath continues. For billions of years, this cycle has kept the planet habitable. It is both fragile and self-correcting, depending on scale. Small disturbances fade quickly, but large ones echo for centuries. A thought experiment brings the scale home. Imagine standing on a beach, watching waves that seem eternal. Now imagine that same beach buried under ice, then drowned under a higher sea, then raised again by tectonic uplift. Each transformation happens in slow motion, yet all are part of the ocean's respiration. The coastline you see today is a temporary boundary in an ever-moving system. Nothing stands still long enough to be permanent, yet the rhythm endures. Why it matters is simple. The breath of oceans is the foundation of every climate pattern, every ecosystem, every story of stability or catastrophe. To monitor that breath is to take the planet's pulse. When the rhythm shifts beyond our models, the consequences reach from coral reefs to harvest fields to the energy that warms our homes. We are connected to this slow respiration whether we understand it or not. The deeper we listen, the clearer the voice becomes. The whisper of waves, the crack of sea ice, the hum of currents measured by instruments thousands of meters down. Together they form a kind of music, a low-frequency symphony that never stops. The planet sings through its fluids, and we have only recently learned how to hear it. At its core, the ocean's breath is also a record keeper. Layers of sediment on the seabed contain microscopic shells that mark each pulse. Oxygen isotopes in those shells reveal the temperature of the water in which they formed. When scientists drill cores from the abyssal plains, they retrieve a million-year timeline of respiration. Warm phases leave different signatures than cold ones. The cores tell us that the breath has quickened in the past century, a sign that the system is under stress. The idea that an entire planet can breathe is both scientific and spiritual. It reminds us that life and geology are entwined. The same process that balances the air for plankton also shapes the conditions for continents to erode and rebuild. To measure the breath is to measure continuity across domains we once thought separate. The ocean does not recognize our boundaries between biology and physics. It moves through them. The future of this rhythm depends on what we do at the surface. The carbon we release, the heat we trap, the rivers we dam, all alter the inhalations and exhalations below. The ocean will adjust, but its adjustment may not favor us. Our task is to learn the tempo well enough to anticipate the consequences of each note we play. As this chapter closes, we stand again at the edge of a moving sea. The tide pulls out with a sigh that has been repeating for eons. Far below, currents twist and coil, carrying stories of heat, salt, and time. Above, clouds form and drift, the breath turning to weather. The next step is to descend from the surface to the hidden archive below, where pressure and darkness preserve what the air and light cannot, to discover what secrets lie in the planet's last great library beneath our feet. The surface of Earth is loud. Winds carve, rivers cut, and continents drift. Yet beneath that clamor lies a quieter place, where stories settle and harden. Deep below, in layers of rock and fluid, time becomes matter. Pressure seals what motion above would destroy. This is the planet's last archive, a realm where memory hides from the cycles that wipe the slate clean. Imagine the descent. A drill rig towers over a desolate plain, its pipes gleaming with grease. The bit begins to turn, biting through sandstone, shale, and salt. Each rotation sends crushed fragments upward in a slurry that glitters with ancient minerals. The smell of oil and heat fills the air. As the bore deepens, sensors whisper of rising temperature, shifting density, and gas bubbles that should not exist. Every meter gained pushes further into a forgotten era. The deeper you go, the slower time moves. Rock becomes a record written in pressure. At 12 kilometers down, the walls sweat moisture that was once the surface ocean. Here, life and heat meet in strange partnership. Microbes inhabit pores in rock older than vertebrates, feeding on hydrogen and methane produced by the Earth's chemistry. They never see sunlight. Yet their existence redefines what it means to be alive. In these hidden cathedrals of stone, biology becomes geology. The boundary blurs until we cannot say where one ends and the other begins. To put it another way, the crust is not solid history. It is breathing stone. Fluids percolate through cracks, carrying chemicals that record the changing balance of the deep earth. Isotopes of carbon, sulfur, and helium drift upward, their ratios betraying events far below. A shift in those signals can reveal a volcanic pulse, a shift in mantle convection, or a surge of microbial activity. Scientists read these clues the way astronomers read starlight, searching for patterns that connect the visible to the invisible. The deeper you drill, the more the familiar world dissolves. Sound changes pitch, heat warps instruments, and the concept of color loses meaning. Yet every fragment extracted from that depth tells a story. A chip of basalt might reveal the composition of an ancient ocean. A vein of quartz may hold water trapped for 1 billion years. Even diamonds, born in the mantle, carry within them specks of graphite that began as living carbon. They are courier envelopes from a world we will never visit directly. Why does this matter? Because if Earth erases its surface stories, this is where some of them flee. The last archive beneath our feet keeps fragments of every age. The chemistry of its fluids speaks of vanished climates. The orientation of its minerals records magnetic fields that flipped long before animals walked on land. The isotopic balance of trapped gases hints at catastrophic events we can scarcely imagine. Every sample brought up is a page rescued from fire. A single drill core might pass through sediments that span 500 million years. The colors shift from red to gray to black, marking oxygen levels in ancient seas. Fossil spores appear, then vanish. Layers rich in iridium signal the impact that ended the age of dinosaurs. Above them lie the ashes of vast eruptions that darkened the sky for decades. Each centimeter of core is a whisper, and together they tell of worlds that rose and fell long before ours. At its core, the crust functions like a vault with a leaky seal. Over time, tectonic forces fold and bury the pages, but a fraction remains legible. To extract those pages, scientists use boreholes as microscopes. Fiber optic cables measure strain and temperature. Seismometers record tiny earthquakes that echo through the rock. The data flow upward in real time, turning depth into signal. From these signals, we build models of the interior, reconstructions of how heat and matter circulate beneath continents and seas. In everyday language, we are learning to hear the heartbeat of stone. That pulse is slow but steady. Each tremor, each microquake, each hiss of gas is a syllable in a long conversation. The planet speaks through vibration and chemistry. We have only begun to understand its grammar. It tells us when magma rises, when fluids move, when faults begin to strain toward release. One day, we may listen closely enough to predict disasters before they surface. Deep drilling projects around the world have become laboratories of time. In Germany's KTB hole, in Japan's seafloor boreholes, and in the depths of Siberia, scientists chase the frontier between accessible and impossible. The deeper the hole, the stranger the results. Instruments record heat far higher than models predicted, rocks rich in unexpected minerals, and microbial colonies that appear where none should survive. The message is consistent. The archive is not dead. It is active, dynamic, and still writing. A pale shade of mystery hangs over this pursuit. What else might be down there? Sealed away by eons of pressure, fossilized remains of early microbial mats tell of the first breaths of oxygen. Layers of black shale mark global die-offs that followed runaway warming. Chemical fingerprints of ancient seawater still shimmer in brines trapped within salt domes. Each find expands our concept of the possible. The last archive is not a cemetery. It is a library still cataloging its books. There is a paradox in that library. The deeper we read, the less human our understanding becomes. We work with data no eye can see, using numbers to translate the weight of stone. Yet the deeper truths are simple. The archive endures because it is buried beyond reach of erosion, wind, and rain. Its only enemies are heat and time. Even they act slowly. If a trace of a vanished civilization were ever to persist, this is where it would hide, not on a mountain face or ocean floor, but deep within rock that forgets slowly. A group of researchers once retrieved a core section from 5 kilometers down. When they split it open, the interior gleamed with crystals that had not seen light in hundreds of millions of years. Inside, trapped in minute cavities, were pockets of fluid. They contained chemical ratios identical to ancient seawater. In a sense, they were bottled oceans, the breath of Earth from a time before mammals. To hold such a sample is to hold the past itself, heavy, silent, and self-contained. Why it matters is both practical and philosophical. Practically, the archive offers the only direct evidence of how Earth's interior evolves. Without it, we would guess at the causes of earthquakes, volcanoes, and continental drift. Philosophically, it humbles us. Beneath every step lies a record too vast for our brief existence to change. We borrow stability from a system that has survived impacts, extinctions, and the birth of continents. The archive beneath is our reminder that permanence exists, but it belongs to stone, not to us. To think of this archive as alive changes our approach. If it moves and reacts, we must treat it with respect. Deep mining and drilling awaken stresses that can trigger tremors. Extraction without understanding risks, disturbing the delicate equilibrium of pressure and fluid that has held for ages. The last archive is a teacher, not a resource. It offers knowledge in exchange for caution. In the dim light of a laboratory, a scientist studies a thin section of rock from that depth under a microscope. What looks inert begins to shimmer with detailed veins of quartz, flecks of pyrite, traces of trapped bacteria. Each inclusion is a door to a different era. The scientist notes the orientation of crystals, the shape of fractures, the ratios of rare elements. The work is slow, patient, and filled with reverence. Every observation is a conversation across time. Think of it like this. The deeper layers of Earth are chapters written in a language of heat and pressure. We decode it through chemistry, magnetism, and sound. When the translation aligns, we glimpse the continuity of the planet's history. When it does not, we know there is more to learn. Either way, the act of reading brings us closer to the realization that we live on a planet still telling its story. Near the end of this descent, the drill bit strikes a region of metamorphic rock so dense that progress nearly stops. The cores that return are banded and iridescent, each stripe a record of compression beyond imagination. The technicians name the deepest sample the memory stone. Its layers ripple under polarized light like frozen waves. Inside those waves lies the sum of forgotten eras, collisions of continents, oceans long vanished, and perhaps traces of substances that no natural process should make. The scientists whisper of anomalies that might mark ancient industry or unknown chemistry. They keep such thoughts cautious, framed in data, but the idea lingers. The last archive beneath our feet is vast and restless. It holds the memory of the planet's breath, the rhythm of its heart, and perhaps the earliest signals of intelligence that dared to touch its surface. We have only drilled the first few syllables of that record. To continue, we must refine our instruments and our patience. What we find next may alter how we define history itself. At the edge of the drill site, the wind rises, carrying dust from a world still alive with change. The borehole stands silent, capped and waiting. Beneath it, the rock continues to whisper. The next step is to follow that whisper into the deeper engine of the world, where heat turns to magnetism and the planet's shield begins to hum, guarding everything that memory leaves behind. Beneath the last archive lies a realm of motion without rest, the true engine of the planet. It is here, in the molten outer core and the solid heart within, that Earth generates the magnetic field wrapping our world. That invisible cocoon shields life from cosmic radiation and guides migratory creatures through the dark. Yet it is not constant. It flickers, wobbles, and sometimes reverses. What we call the magnetic shield is in fact a restless storm of metal and motion, born from heat that has been flowing outward for 4 billion years. Imagine the structure from center to surface. At the heart lies a sphere of iron and nickel about the size of the moon, solid because of crushing pressure. Surrounding it is a sea of molten iron, swirling like a planet within a planet. The heat released as the inner core slowly grows drives convection in that liquid metal. Electrical currents form as the conducting fluid moves through existing magnetic fields, and those currents in turn generate new fields. The process feeds itself, a feedback loop called the geodynamo. It is the hidden engine that turns motion into magnetism. To put it another way, the planet's shield is a side effect of its attempt to cool. As heat escapes from the core toward the mantle, it stirs the metallic ocean below. That movement produces magnetism, and magnetism deflects charged particles streaming from the sun. The auroras we see at night are visible scars of that defense, curtains of light that ripple where the field lines meet the atmosphere. Without this shield, solar wind would strip the air and water from Earth as it did from Mars. Life owes its persistence to the dance of liquid iron below our feet. The evidence for this engine comes from both measurement and magnetized stone. Sensitive satellites orbiting Earth record subtle changes in field strength from year to year. They show that the magnetic poles drift, sometimes by tens of kilometers annually, and that the field occasionally weakens before rebuilding. In ancient lava flows, minerals align with the prevailing direction of the field at the time they cooled. When those rocks are dated, they reveal a history of reversals occurring irregularly across millions of years. The pattern is chaotic yet self-renewing, proof that the engine has never truly stopped. A plain language view of this complexity helps. Think of a pot of water heated from below. The hotter it becomes, the faster the currents form, and the more unpredictable their paths. The core behaves the same way, except its fluid is metal, and its convection cells are thousands of kilometers wide. These swirling eddies create overlapping magnetic fields that combine to produce the one we measure at the surface. When the flow reorganizes, the field weakens or flips. The process takes centuries, but the change is global. Compasses would slowly point south instead of north. Why does this matter? Because every reversal or fluctuation leaves a fingerprint in rocks and sediments. That record allows scientists to synchronize layers across continents and oceans. It is the planet's built-in timestamp, marking epochs with magnetism rather than ink. It also reveals that the dynamo responds to conditions at the boundary between core and mantle. When the heat flow changes, so does the vigor of the magnetic field. Our planet's heart and crust are not separate systems. They communicate through convection and time. Above the dynamo sits another engine, one powered by rotation and sunlight. The atmosphere and oceans interact with the magnetic field, coupling charged particles and currents in ways we are still deciphering. Lightning, cosmic rays, and even human power grids can influence small regions of the magnetosphere. We live inside a web of interactions between core, crust, air, and space. Every thunderstorm and every solar flare is a reminder that the shield is both protective and permeable. A question rises from this understanding. How stable is the field that guards us? Measurements over the last century show a gradual decline in overall strength of about 10%. This does not mean collapse is imminent, but it suggests that the system is always evolving. Geological records confirm that field intensity has fluctuated many times before without catastrophic loss. Still, a weaker field would allow more radiation to reach the upper atmosphere, altering satellites, navigation, and even climate chemistry. The shield does not vanish, it flickers, and we must adapt to its rhythm. Deep within, the inner core itself may rotate at a slightly different rate than the mantle and crust. Some studies suggest it lags, others that it races ahead by a fraction of a degree per year. This differential motion could influence the shape of the field and the pattern of reversals. The idea remains debated, but it highlights a truth about the engine. It is not a single spinning mass, but a layered machine with parts moving at different speeds. The hum we feel through magnetism is the resonance of those mismatched rotations. Why it matters extends beyond geomagnetism. The stability of our climate and technology depends on this hidden engine. Solar storms occasionally compress the magnetosphere, releasing energy that can induce currents in power lines and pipelines. Understanding the field's behavior helps protect modern infrastructure. On a deeper level, it connects us to the long history of planetary evolution. The same process operates in other worlds. Jupiter's powerful magnetosphere, Mercury's weak one, and Mars's absent shield all reflect variations on this internal theme. The The geodynamo is a universal language of planetary life. Consider what the shield has preserved. It kept the early atmosphere dense enough for water to remain liquid. It allowed DNA to evolve without constant radiation damage. It made possible the long continuity of surface life. Each flare deflected, each storm absorbed, was an act of protection delivered by molten motion we will never see. The engine beneath us is anonymous yet intimate. It hums through every compass needle, every aurora, every quiet night when cosmic rays fail to reach us. In a laboratory on the surface, researchers attempt to simulate the core in miniature. They fill spherical vessels with liquid sodium and spin them while applying heat and rotation. Magnetic sensors around the spheres detect fields that rise and fall chaotically, occasionally flipping polarity. These experiments confirm the theory: turbulence alone can generate organized magnetism. It is a humbling insight that order can arise from chaos, that a field strong enough to envelop a planet can emerge from simple physical laws acting over immense scales. To think of it in simpler terms, the planet is an enormous generator. Its rotation is the crank, its molten metal the coil, and its magnetic field the current. Unlike any machine we build, it never powers down completely. It pulses, stalls, and revives. But the motion continues. When we stand under the dancing light of the aurora, we are seeing that current leak into the upper atmosphere, a reminder that even the shield occasionally sings. The connection between engine and archive is profound. Magnetic minerals in the crust act as tape heads recording the state of the field at the moment they formed. Each reversal etched into basalt or sediment becomes a clue to the history of the dynamo. The rocks are the memory of the engine, and the engine is the power that wrote the rocks. Energy and record entwined, one preserving the other. A quiet realization follows. The same shield that guards life also hides its traces. When the field reverses, radiation increases, species adapt, and some vanish. These periodic stresses may even shape evolution. The dynamo gives and takes, sculpting the story of biology as surely as it shapes the geography of the magnetic poles. In this sense, the engine is not merely mechanical. It is a participant in the drama of life. At its core, Earth's protection is a balance between order and turbulence. The shield's beauty lies in its instability. It shifts, reforms, and continues, like a heartbeat that never quite repeats. We read its changes through lava, through compass drift, through the faint tremor of satellites crossing its boundaries. Every measurement reminds us that the surface world rests on an ocean of fire, whose music we only faintly hear. Night over the poles offers a view of this hidden architecture. Curtains of green and violet ripple across the sky, tracing the field lines that dive toward the surface. Each curtain flickers as charged particles strike oxygen and nitrogen atoms, releasing photons. It is the living proof that our world is connected from core to atmosphere, from metal to light. The aurora is not decoration. It is communication between layers of the planet that seldom speak in visible form. So the story of engines and shields is not a tale of safety, but of endurance. The field will waver, the poles will wander, but the planet will keep breathing. The same heat that drives the dynamo will continue to leak outward, slowly powering volcanoes, ridges, and the tectonic motions that renew the surface. All of it is one continuous circuit. The memory stored in stone owes its existence to the heart of liquid fire beneath. As this chapter closes, we stand at the threshold between core and cosmos, listening to the hum of the generator that keeps both in balance. The next step is to follow the shield outward, to see what traces of our presence or any other might survive beyond its reach. On worlds where the archive is safe from wind, rain, and time, waiting in silence for discovery. The deeper we explore, the more a question returns. Quiet but insistent, if the planet has erased so much of its own story, how would we recognize a civilization that lived and vanished before us? The Silurian Test was born from that question. It is not a fantasy or a myth. It is a scientific thought experiment, an audit of the geological record for unnatural patterns. The idea is simple in phrasing but immense in scope. Could the fingerprints of industry survive the passage of millions of years? And if so, what would they look like? The name comes from a time period 450 million years ago, long before mammals or trees, when fish first grew jaws and coral reefs flourished in shallow seas. No evidence suggests there were intelligent beings then, yet the Silurian Test borrows that epoch as a stand-in for any forgotten chapter. The test asks a disciplined version of a haunting question. Could another species have risen, changed the planet, and been buried without leaving a trace we recognize? The first rule of the test is humility. Human artifacts would not survive in recognizable form after a few million years. Metal rusts, concrete crumbles, glass weathers, and plastics degrade into invisible residues. The crust is constantly recycled. Within 10 million years, nearly every surface structure we have built would vanish. Only chemistry could remain. Our challenge is to find the kind of chemical or isotopic signals that no natural process can easily mimic. To put it another way, the Silurian Test is an exercise in forensic geology. Instead of seeking monuments, it searches for patterns. It looks for shifts in isotope ratios, anomalies in sediment composition, and traces of synthetic molecules that resist decay. The aim is not to prove that a prior civilization existed, but to verify whether such an existence could be detected at all. A negative result still teaches us how fragile our own memory will be. The reasoning begins with carbon. When a civilization burns fossil fuels, it releases carbon dioxide with a distinct isotopic signature. Carbon from ancient sources is depleted in the heavier isotope, carbon-13. A sudden global drop in the carbon-13 to carbon-12 ratio would mark a rapid injection of old carbon into the air, exactly what humans are doing now. If a similar spike appeared in rocks tens of millions of years old, we would have to explain it. Volcanoes and methane bursts can create similar signals, so the test requires multiple lines of evidence before drawing conclusions. Next comes temperature. Global industry warms the planet, and that warmth leaves fingerprints. Sediments deposited in warmer oceans show differences in oxygen isotopes within microscopic shells. If an ancient industrial episode occurred, the pattern would appear as a sharp, short-lived thermal spike followed by a gradual recovery. In the geological record, one such event already stands out: the Paleocene-Eocene thermal maximum. The Silurian Test re-examines that period with cautious curiosity. Could the spike have been natural, or could it have contained an unrecognized signal of activity? In everyday language, the test functions like a checklist. We scan for rapid changes in climate, carbon, and biodiversity that cannot be fully explained by known natural mechanisms. We examine metal distributions for enrichment in rare elements like platinum or osmium that could come from industrial processes. We search for synthetic molecules such as certain plastics or chlorinated compounds that resist breakdown and might fossilize as thin chemical films. We analyze magnetic grains for unusual alignments caused by artificial heating. Every anomaly is a question mark. Why does this matter? Because in searching for hypothetical ancestors, we also discover how to measure ourselves. The same methods that might detect an ancient civilization's impact can track our own. When we analyze deep sea cores for industrial signals, we are also watching our footprint spread through the strata. The Silurian Test turns archaeology into self-awareness. Its most important finding may not be a hidden civilization but a mirror. A team applying this test once analyzed sediments from the South Atlantic, cores spanning 60 million years. Within those layers, they found sharp increases in heavy metal concentrations, brief peaks in carbon isotopes, and microfragments of unknown polymers. Each clue by itself could be natural. Together, they formed a pattern disturbingly similar to the modern Anthropocene. After months of review, the team concluded the signals were coincidental, produced by volcanic eruptions and ocean chemistry shifts. The mystery dissolved, but the method improved. Even failure refines the lens. At its core, the Silurian Test is a map of skepticism. It warns us against assuming that absence of evidence is evidence of absence, yet it demands discipline before imagination. The Earth is full of mimicry. Natural processes can fake industrial patterns. The test asks that we filter fantasy through measurement, speculation through reproducible data. In doing so, it extends scientific rigor into the oldest question humans have: are we alone? Not just in space, but in time. Another layer of the test expands beyond Earth. Our neighboring worlds, especially the Moon and Mars, lack the recycling mechanisms that erase history here. Lunar dust has no weather, no plate tectonics, no erosion by water. If an industrial age ever touched Earth, debris might have escaped into orbit and landed there as microscopic fragments of aluminum or glass. These would remain frozen in the regolith. Mars, with its thin air and slower geology, could hold similar clues. The Silurian Test, therefore, includes an extraterrestrial component. The search for Earth-made artifacts outside Earth itself. In laboratories, scientists simulate deep time burial of synthetic materials. They heat plastics, metals, and electronic waste under pressure to see how they would transform. Some compounds break down into simple carbon chains that blend with organic matter. Others form stable crystals that could persist indefinitely. The results suggest that while most modern artifacts would vanish, a few might survive as unrecognizable minerals. The fossil of technology may not look like technology at all. It may appear as an unfamiliar rock with a strange ratio of trace elements. The next question is philosophical. If we did find such a signal, what would it change? The existence of a prior civilization would not lessen our uniqueness. It would deepen the story of intelligence in the universe. It would show that consciousness can emerge more than once on the same world. It would also serve as a warning. If they rose and vanished without leaving a clear mark, it means longevity is not guaranteed. The Silurian Test, in this sense, becomes a study of impermanence as much as detection. Simply put, the search for predecessors teaches us how to preserve our own signal responsibly. We cannot choose to be invisible. Our chemistry already stains the rocks. But we can decide what kind of signature we leave. Do we mark the strata with pollution and loss, or with stable, recoverable traces of knowledge? Could we encode a message in durable isotopes or patterns recognizable to future scientists, a beacon that says we learned from our past? Why it matters reaches beyond curiosity. The tools of the Silurian Test sharpen our ability to read any world's history. They may one day help us identify artificial climate shifts on exoplanets, distinguishing life-driven change from natural cycles. In that future, the test becomes a universal method, a way to recognize intelligence by its geological handwriting rather than its monuments. The idea bridges planetary science, ethics, and imagination. In a quiet research center, a small group of analysts reviews a graph projected on a wall. The line rises sharply, then falls. The pattern matches the carbon curve of our own age. Yet the layer represented by the sample is 60 million years old. The team argues gently. Could it be an error, a calibration drift, or something worth rechecking? They schedule new sampling, knowing that even if the anomaly fades under scrutiny, the act of looking keeps science honest. The Silurian Test thrives on such caution. It treats every hint as both promise and trap. Think of it like this. The Silurian Test is a mirror we lower into time. We look for reflections, knowing that some may be ours. The rocks do not lie, but they speak a language of chemistry that requires patience to translate. Each potential signal is a syllable, each layer a page. When read together, they form a story of a planet that keeps secrets, yet offers them to those who listen. The test has no ending because the archive is never complete. New cores will be drilled, new instruments will refine detection limits, and one day we may find a pattern that forces us to reconsider history, whether that pattern points to others or only to ourselves. It will remind us that intelligence is part of geology now. We are no longer separate from the planet's processes. We are one of them. The Silurian Test invites both skepticism and wonder. a pairing rare in science. It tells us that the world forgets but does not lie, that traces of any civilization, past or future, must pass through the same filters of chemistry and time. The lesson is not how to prove the existence of predecessors, but how to ensure that our descendants, human or otherwise, will find enough truth in the rocks to know we cared to ask. As we close this investigation, we step from the deep cores and quiet labs into the larger silence of space. Beyond the shielded Earth lies the moon, patient and untouched, its dust holding every impact since the beginning. The next step is to turn our search outward, to those unchanging surfaces that may hold what our restless planet cannot, where the last whispers of lost civilizations or our own future echo may wait for the right eyes to find them. When the drilling stops, when the last core is lifted and sealed, what remains is not silence, but perspective. We have followed the trail of memory through stone, heat, and magnetism. We have watched how Earth builds, forgets, and rebuilds itself, how oceans breathe, and how the magnetic shield hums around all living things. The picture that emerges is vast and impersonal, yet within it lies a pattern that feels strangely familiar. A planet's life is not so different from our own. It learns through repetition. It preserves what it can, and it lets go of what no longer fits. Standing back from this long investigation, one truth becomes clear. The surface world is only a reflection of deeper forces. Our continents, our weather, even our sense of time depend on the engines below. The rocks we call ancient are transient skins. The air we breathe a temporary mixture of gases drifting through geological lungs. Earth is not a stage for life. It is part of life. We are a late expression of its chemistry, a fleeting arrangement of the same atoms that move through mountains and seas. In plain terms, we are the planet thinking about itself. Every observation, every core sample, every line of data is the crust becoming aware of its own history. That awareness is fragile, but it matters. To look into deep time is to glimpse a mirror so old it barely resembles us. In that reflection, we see both the rarity of our moment and the inevitability of change. The Earth has survived impacts, extinctions, and reversals. It will survive us as well. The question is not whether the planet will endure, but what kind of memory it will carry forward. The Silurian Test leaves us with an uncomfortable symmetry. If the signs of earlier industry would vanish under erosion and subduction, so will ours. The layers we build today, the plastics, the isotopes, the altered climates, will one day compress into a thin horizon of anomalies. To any future intelligence, that horizon will look like a fever, brief and bright, a chemical flare on a long and steady record. Our monuments will not speak, but our atmosphere will. The rocks will remember not our faces, but our chemistry. Why does this matter? Because it changes how we define legacy. For most of history, humans have measured permanence by the endurance of stone, of words carved into cliffs or temples. Now we understand that real permanence lies in the invisible signatures we leave behind. A change in isotope ratios, a subtle shift in magnetic grains, a layer of soot that never fully disappears. These are the true records of our civilization. We cannot choose whether to leave them, only how to shape their meaning. At its core, the story of Earth is the story of transformation. The crust melts and reforms. Oceans appear and vanish. Life evolves, diversifies, collapses, and begins again. Nothing stands still long enough to be preserved unchanged. Yet the cycle itself is constant. We are part of that cycle, participants rather than exceptions. Our species has learned to accelerate change, but not to escape it. The power we wield is borrowed from the same thermodynamics that drive volcanoes and tides. Think of the magnetic field that protects us. It flickers, reverses, and rebuilds itself, yet it never stops. The planet's heart is a master of renewal through instability. That rhythm may be our best metaphor. Societies collapse and reform. Knowledge is lost and rediscovered, but awareness persists in fragments. Like the dynamo, culture regenerates itself from motion and contrast. The instability that threatens us is also the engine that creates understanding. There is a moment in every excavation when a geologist holds a fragment of rock and realizes that it was once part of something alive. The distance between biology and geology vanishes. The carbon that fed a forest now lies locked in limestone. The same atoms that once formed leaves now hold mountains together. It is not reincarnation in the mystical sense. It is chemistry's quiet form of continuity. Every breath we take carries molecules once exhaled by other species, perhaps by other worlds. Matter never ends. It only moves through new arrangements. In the darkness of the deep archive, where pressure turns everything to patience, the idea of civilization itself shifts. No culture can last forever, but intelligence may reappear wherever conditions allow. The Silurian Test becomes more than a search for predecessors. It becomes a meditation on recurrence. If thought can arise once, it can arise again. Perhaps intelligence is not a single flame, but a property of complexity, inevitable whenever matter is given enough time to organize. In that sense, we are not alone, even if no others are visible. The ethical weight of this realization is immense. Knowing that the planet forgets forces us to decide what to try to preserve, not in monuments or archives, but in behavior. Our influence on the climate, on the chemistry of air and sea, is now part of the Earth's metabolism. We can act with the awareness that every decision becomes geology. A bridge we build, a forest we burn, a particle we release, all join the slow circulation of matter. Our lives write in the same alphabet as tectonic plates. Simply put, we are temporary stewards of a very old memory. The ground beneath our feet has recorded extinction and recovery many times. It has seen oxygen rise, carbon fall. Continents join and drift apart. If we wish to endure, we must learn to live at the pace of that memory. Short-term goals, measured in years or elections, fade against the cadence of deep time. Only actions aligned with the planet's long rhythms have a chance of meaning. There is beauty in accepting that scale. The night sky above the shield, the auroras dancing along magnetic lines, the glow of city lights mirrored in them, all belong to the same current. What we call progress is a pulse in that current, a local brightening. Our technology, from satellites to sensors, is how the planet watches itself. Even our failures teach. When a species alters its own climate, it exposes the feedbacks that bind biology to physics. Awareness grows through error as much as through insight. A scientist once said that the ultimate archive of humanity might not be on Earth at all, but in the dust that escapes into space. Each rocket launch, each eruption, sends traces of our world beyond the atmosphere. A grain of paint drifting in orbit could outlast entire civilizations. In that idea lies both comfort and humility. Our story is already leaving the planet, mixed with starlight and radiation. Even if Earth forgets us, the universe may keep a microscopic echo. Why it matters can be expressed in one sentence. To study the planet's past is to practice empathy across time, the same compassion we extend to future generations. We must extend backward to the worlds that came before. They may not have been conscious, but they were stages in the same unfolding experiment of matter becoming aware. We are not the beginning of that experiment, nor will we be its end. Think of it like this. The Earth is a palimpsest written by heat and water, rewritten by life, and now annotated by thought. Every layer adds complexity, and no layer is final. The meaning of our age will not be decided by how long we last, but by what we contribute to the next rewriting. If we can learn to see ourselves as one chapter rather than the whole book, we may guide the next chapter with care instead of fear. The philosophical echo of this realization is quiet but persistent. Time is not a straight line leading away from us. It is a circle of renewal. The atoms that make us will one day form other minds, other questions, perhaps even other civilizations. The true continuity of intelligence is material, not cultural. In that continuity lies a kind of immortality that requires no monuments, only respect for the processes that continue after we are gone. At the edge of the magnetic field, the aurora fades into dawn. Satellites trace the planet's curve, collecting data that will become the next archive. Below, the crust cools, the conveyor moves, and the oceans breathe. The planet remains busy with its remembering and forgetting. We stand within that motion, brief custodians of its awareness, knowing that one day the record of our own age will turn to dust and pattern. Yet somewhere in the future, perhaps millions of years from now, another observer may hold a piece of rock and notice a strange ratio of isotopes, a pattern too ordered to be chance. They will ask who we were, what we knew, and why we left. The answer will not come from monuments, but from the chemistry of the stone. In that quiet recognition, across the gulf of ages, the Earth will have spoken once more through us. The open question lingers, as wide as time itself. If awareness is the planet's latest experiment, will we prove worthy of being remembered by the very world that taught us how to remember?